Welcome. Thank you for joining our webinar. For today's topic is production of high precision pump parts and EMAG solutions for driving. My name is Jeff Moore, one of the regional sales managers here in Canada and the USA. I'm joined by my colleagues from Germany, Matt Winkler and Yannick. There will be a section in the chat to ask any questions that you have during our presentation. And then there's also a section for questions. If you want to take a question in there, we'll answer it each positive section of the presentation. With that, I hand it over to Mr. Winkler. Yannick, thank you.
Okay, Jeff, thanks for your introduction. As Jeff already mentioned, my name is Manfred. I'm head of the technical sales in the business unit grinding in the EMAG group, and I will guide you through this webinar together with my colleague Yannick. So here are the contents of this webinar. The first point is you get some information about the motivation of this webinar. The second part is the bigger part. We will introduce our VG110. It's a vertical non-round grinding machine for small hydraulic parts. The next point, these are our VLC series. These are bigger machines. On this machine, we will show you also two applications for non-round grinding and a combination. Then you will get some information about the EMAG contour. It's a software for non-round grinding. And at the end, we make a summary. So let's start. What's the motivation of this webinar? According to a study by Growth Market Reports, the global pump market is a growth market with an annual growth potential of around 4% until 2031. Pump systems are not visible at first glance, but very important in a variety of applications in our daily life. So you find pump systems in cars, in commercial vehicles, in vehicles for agriculture, for construction, but you can find this also in our household applications or in some heating applications. The increasing demand for energy efficient pumps is likely to boost demand for pumps on the market. Therefore, the pump market is an interesting market area that differs from other market areas which currently have stagnation or decline in terms of growth. That's the reason why we go now to the pump market. And now we come already to the second point of our webinar for the VG110, and I hand over to Yannick. Yannick, please.
Thank you, Manfred. Welcome, ladies and gentlemen. My name is Yannick. I'm responsible for the Department of Technology at the business unit grinding in Saarlach. I will now introduce you to our machine concept VG110, optimized for the production of small non-round geometry parts up to a workpiece diameter of 110 millimeters. I will show you two use cases, two application examples that we realized with our customers, a pump ring for hydraulic application and rotor and stator of a steering pump for an agriculture vehicle. The VG110 is a really compact solution for the grinding process, as you can see in relation to the size of the operator's panel. We have a very small footprint of the machine, just a machine width of 1.4 meters, so the machine requires very less space in the production shop floor. The workpiece portfolio that can be machined with these machines includes rotors and starters for internal gear pumps, pump ring for vane pumps. We will focus on this in this chapter, but also for parts, for non-round parts for camshafts, for example, can be ground on this machine. We start with the core component of a vane pump. The pump ring, its contour accuracy and also its surface quality significantly influences the noise emission in the application and also the energy efficiency. So in this application, a grinding process that is designed for its optimum does not only save resources in the production of the part, but also in its application, because the energy consumed for pumps with good quality is much lower. So we have a positive influence on the whole life cycle of pump parts. The function of a vane pump I'd like to explain on this slide. In red, in this sketch, you see the pump ring. Its non-round geometry will be ground on our machine. In yellow, you see the rotor with the single vanes. The vanes are mounted in small nuts, and by means of springs, there's always contact between the vane and the non-round pump ring. So we have separate fluid chambers which are responsible to generate pressure in the pump. You can see it here. On the inlet side, we have an increase of volume in the fluid chamber according to the non-round geometry, and on the right side, the volume gets smaller, so we have a compression there. We generate the pressure. This is how the part looks, made of steel. The pump ring is fixed in a housing. You see here the flat grounded surfaces, and in these two areas, these are the inlet areas where the fluid comes in, and in the fluid chambers separated by the vanes, we have a pressure buildup. What is the machining task for this part? The workpiece is made of hardened 100 chrome 6 or sinter metal D32. We have to grind the inner contour, and we have to remove a grinding allowance of 0.8 millimeters in diameter. The biggest challenge in this context was to achieve an average surface roughness of 0.2 microns, while we have to machine a very high grinding allowance, nearly 1 millimeter. Of course, there are some requirements with regard to position and profile. Position deviation must be lower than 50 microns, the profile deviation lower than 20 microns, a straightness deviation maximum 2 microns, and a perpendicularity of maximum 7 microns is required. The basic machine concept of the VG110 bases on decades of experience at EMAG with vertical grinding machines, also with other combination technologies for fine machining. The customer or his workpiece handling system positions the raw part at the workpiece shuttle in horizontal orientation, and next to this position he gets the finished part after grinding. The workpiece shuttle brings the part into the machine, so it is the interface to the surroundings. The workpiece lift is responsible for the angular orientation of the part and lifts it up to the clamping device, which is fixed on the workpiece spindle. The workpiece spindle is moved in X direction and brings the part into the machining area, where we find two internal grinding spindles which are moved in Z direction towards the part. In case that we use vitrified grinding wheels, they are dressed in the machine, and the dressing spindle for this purpose is mounted on the workpiece spindle. Now we have a look at an automated solution for this machine concept. You see the workpiece handling brings the raw part to the shuttle and gets the finished part after grinding. Once again, raw part is positioned on the shuttle, and the finished part is removed from the position for the finished part. The workpiece lift brings it to the chuck, and now the grinding process takes place. As you can see, we're using 3D printed cooling nozzles to make sure that the coolant is on the correct position especially for internal grinding applications. This is very crucial to make sure that there is no grinding burn for high material removal rates. The grinding wheels can be dressed in the machine. We use a rotary dressing spindle with a maximum rotational speed of 16,000 revolutions per minute. We have a touch sensor system based on acoustic emission to find the first contact between dressing wheel and grinding wheel, and to make sure to dress the grinding wheel as less as possible, but also make sure that we get the required sharpness of the wheel. We are able to achieve with this rotational speeds the common ratios of dressing speed, which makes the process very robust. The diameter of dressing wheel in this application was 80 millimeters. Our grinding strategy is based on a two-step grinding process. First, we did a pre-grinding process to remove as much material as possible with a very high feed rate. For this purpose, we used an electroplated CBN grinding wheel. The non-round geometry was realized by an interpolation of the x-axis and the rotating c-axis. After getting very close to the final geometry, we used a finish grinding process for the inner contour to make sure that the shape deviation is as less as required, and also to make sure that the surface roughness of 0.2 microns was achieved. Here we use the vitrified CBN grinding wheel, which has been dressed in the machine. The grinding wheel diameter was 16 millimeters in this application, and the width of the grinding tools 20 millimeters. We used oil as coolant. It is very important to mention that the viscosity should be not higher than 5 centistokes, because it's very dangerous to get an aquaplaning effect. We have a very large area, very large contact area between the small grinding tool and the workpiece, and an oil with a higher viscosity can lead to high normal forces, which causes shape deviations of our part. We achieved the following cycle times for 100 chrome 6, 40 seconds, which includes loading and unloading of the part, and of course the 2 grinding steps. Because of the better machining behavior for the sinter metal part, we achieved a cycle time of 32 seconds. All in all, annual quantity of 450,000 parts could be machined with this concept. The achieved quality is also shown here. Line deviation, straightness deviation was lower than 10 microns, position deviation lower than 30 microns, perpendicularity smaller than 5 microns, and the biggest challenge in this context, average surface roughness was achieved with lower than 0.2 microns. Another application example where surface and geometry quality is also very important are G-rotor pumps, also known as internal gear pumps. You find them in many hydraulic applications, agriculture, forestry machines, construction machines, but also in equipment for garden, or even in consumer goods we find hydraulic systems. The functional principle of this part is a bit different. We achieve an increase of the fluid volume at the inlet side by the geometry of rotor and stator and the required relative speeds. So you can see we have an increase of volume on the inlet side, and then the chamber volume gets smaller, so we have a pressure build-up. This is the reason why in this case, especially the geometry of the part and its shape deviations are very important for the application behavior. For the rotor, we had to grind the external contours. Material was steel 100 CR TIC, harden it up to a Rotnell hardness of 63. The stock allowance for this application was 0.8 millimeters. The accuracy of the finish diameter plus minus 6 microns, we have to achieve an average surface roughness of 0.5 microns, profile deviation lower than 6 microns, parallelity of the part referring to the B-axis lower than 12 microns, perpendicularity in this case maximum 15 microns, and also the angular deviation, quite challenging for the angle between the peaks of the polygon. With regard to the stator, we have to grind the inner contour of this part. Same material, same hardness, slightly lower grinding allowance, and also similar requirements with regard to surface roughness and shape deviation. What was the strategy for this grinding application? We first did a pre-grinding process. The aim was to achieve a very high material removal rate, then do an intermediate measurement procedure with an integrated probe in the machine, do the correction of the diameter, and then carry out a finish grinding process to make sure that the surface and geometry quality is according to the requirements. For the external grinding process of the rotor, also interpolation of X and C axis took place. We used a vitrified CBN grinding wheel. We did the orientation in angular deviation according to the gearing inside, and then we did axial clamping on the workpiece spindle. The geometry allowed us to use a grinding wheel diameter of maximum 16 millimeters. For the inner contour grinding process, as you can see, the geometry only allows a vitrified CBN grinding wheel with a maximum diameter of 7.4 millimeters. The grinding wheel width in both cases was 26 millimeters, chosen according to the width of the workpiece. Same coolant was used, oil was maximum 5 centistokes, and this resulted in a cycle time of 110 seconds for the rotor, which includes loading, unloading, the measurement, and the 2 grinding process steps. For the stator, it was 120 seconds. Depending on the workpiece geometry, especially depending on the width of the workpiece, it would even be possible to grind more than one part in one operation. We would use a package and clamp this in the chuck, possible up to a width of 35 millimeters for this geometry. In case that we are able to use bigger grinding wheel diameters, then even thicker packages would be possible to machine. The straight deviation that we achieved was 6 or 10 microns, perpendicularity also according to the requirements, and the surface roughness lower than 0.5 microns. As already mentioned, the workpiece shuttle is the interface between machine and surroundings, can be operated by manual loading, or you can also discuss with EMAG our in-house workpiece handling system to do an automated loading of the machine. Before I finish this chapter about VG110, I like to summarize the main features of this machine. We have a very high vibration damping because we use our mineralite machine base. This enables us to achieve a long tool life and high surface qualities. Because of our vertical spindle orientation, the chips can fall down into the dust collector. We reduce the interface between abrasive particles in the machine and with the machine axis to a minimum. We have short-to-short chip times because of our integrated automation by means of the workpiece shuttle and the pickup spindle. We have a very small footprint, so we need very low space in your production, and the accessibility of the grinding spindles and also the clamping device is very good. You can open the front door. You have a perfect overview of all the important parts and components of the machine. So this makes it easy to do the setup for different geometries, for different applications, and also 2 grinding spindles give us a high flexibility with regard to the workpiece geometry. So at this point, I think it makes sense to have a look in the question chat. Maybe there
Yes.
are already some
Questions already
open
coming.
points.
Yannick, the first question is, which raw part quality is required for machining pump rings?
As usual for a grinding process, of course, we wish to have a raw part geometry which is very close to the finish part geometry. This gives us the opportunity to reduce cycle times when we grind a very small grinding allowance. But with regard to the requirements of the geometry, especially to the perpendicularity, because we have to pay a lot of attention to the flatness of the contact area, which is the reference in our clamping device. So usually the parts should be double side ground before our internal and external grinding processes.
There is a next question. What is the minimum quantity for an automated machine?
Of course, this is a question which is difficult to answer in general, because it depends on the cycle time for your individual part. It depends on the labor costs on your location and so on. So this is a question that should be discussed in much more detail with our experts at EMAG LLC, Jeff colleagues, or especially our colleagues from the technical sales here in Saarlach. They will find the correct answer for your individual machining task.
So the next question, pump components have a very different geometries. How can a quick retooling of the machine be ensured?
Yeah, we absolutely agree. Of course, there is a big variation of geometries, a big variation of quality requirements. The first advantage is that our machine is equipped with the 2 spindles. As shown in the last example, we can set one spindle for external grinding. The other spindle can be set for internal grinding. We have a huge flexibility in this context, and also the vertical principle gives us the opportunity to reach all the relevant parts, all the components, to change them, the clamping device, the chuck, and also the grinding tools. We have a good overview, make sure that everything is correct, that we can start the process after setup, and we are sure that we do not cause any crash or other problems.
So there is another question. Are only CBN grinding wheels used in the machine, or is it possible to use corundum grinding wheels as well?
In general, it would also be possible to use a corundum grinding wheel, but as we have got very small grinding wheel diameters, we have just a small number of grinding grains which have to perform the machining work. So there are high loads on these few grains, which causes a lot of grinding wheel wear. So it is absolutely makes sense for these applications, especially for high batch sizes, to use ceramic grinding wheels, super abrasives for steel. But the other aspect is that we have very high temperatures for internal grinding, because we have a long contact arc between grinding wheel and workpiece. CBN has a very good split ring behavior. It always generates sharp cutting edges during production, which reduces the temperatures. Also, CBN has a very good thermal conductivity, so the heat also can flow via the grinding grain into the tool, which also enables us to have a cool situation in the contact zone. So our recommendation for the applications that we've seen today is clearly to use a CBN grinding wheel.
Okay, and now the standard question of each webinar: how long is the lifetime of the tool? How many pump rings can be machined?
Okay, same as for the question with regard to the automation system. It depends on the workpiece geometry. It depends on the cycle time. It depends on the grinding allowance. We have a lot of information of successful grinding processes in our data banks. So we can do very good approximations if we get as much information as possible for the individual grinding task. So this is something that can be discussed with our colleagues in more detail. We kindly invite you to contact you in case that there are concrete applications.
Okay. So, Yannick, thanks for answering the question. Now we go forward with the next chapter. Now we are talking about the VLC series, non-round grinding and combination machining. Now we come to another machine concept, and I will show you two applications. One is a non-round grinding of a housing integrated cam ring, which you can find in radial piston pump. And the second, it's a combination, it's a grinding and brushing process of a control plate, which you can find in the axial piston pump. So here on the right side, you see a housing integrated cam ring. On the picture, you see already these are workpieces from the dimensions are much bigger like before. And here inside this housing, this cam ring, many radial pistons are moving up and down to realize the suction and pressure function of a pump. Let's have a look in this principle. The contour of the cam ring determines the radial stroke movement on the pistons, which result in a constant volume flow on the pressure side without any pulsation effect. So let's have a look about the workpiece details and the machining requirements. Here you see already the OD 232 millimeter, and the width of this part is 108 millimeter, and the weight you can see in the left table, it's 16 kilogram. So this part's already much bigger. The material of this housing is a hardened 50 CRMO4 with a hardness 58 to 63 Rockwell. And here the machining, what we have to do, it's colored in red. There is one side, this is the inner contour. Here inside what we have to grind, we grind the face and we grind also the OD. Interesting is the big grinding allowance what we have in the inner contour. It's 0.8 millimeter in diameter, and if you have such a big ID diameter inside with 190 millimeter, you can imagine it's a big volume which we have to grind. The request on the drawing was RA 0.4, special the contour quality over 360 degrees with 50 microns, the straightness of the inner contour of 5 microns, and the perpendicularity of 20 microns to basic A, which is the front face which we are grind. These are special qualities. So what's the machine concept? Here we use our VLC 350 GT machine. This machine is a multiple technology machine. because you can use inside many different technology units. On the right side on this picture, you see some standard picture. On the right side, we have a turret for turning tools. You have an ID spindle in and an OD spindle in. And this machine concept, we have the same machine bed. It's made from mineralite, like what we have already before on the VG110. And as I told you already, the big advantage is if you have a workpiece, you can combine the best technology, different technologies, which you can use in one clamping to get the best workpiece quality. Here, some words for the design. We have a x-axis, and we have here the workhead, and the x-axis move the workhead and the chuck from the loading area inside in the machine, and after machining back for unloading. We have a z-axis. This is a concept of the pickup concept of EMAG, and special here we have a conveyor system where you have approximately 20 pallets where the operator can place the raw and finished parts. And inside in the machine here special we have 3 grinding spindles, and with this concept it's possible to make a non-round grinding, a round and a face grinding process in the machine inside. Here we see the grinding process chain. We start with the inner contour grinding. This is a non-round grinding process. We have interpolation between the linear x-axis and the rotation z-axis, and we use the vitrified CBN grinding wheel. The second is the face grinding. On the face grinding we use also a vitrified CBN grinding wheel, but this was a special specification. It was a self-sharpening specification. The meaning is it's not necessary to dress this grinding wheel because it's self-sharpening. And the third grinding process what we have, it's a OD grinding. It's a cylindrical grinding, and based on the request that we have to reach OD quality of less than 10 microns, we make a pre-grinding, we make a measuring, and then the finish grinding. And for this third process, we are using also vitrified bonded CBN. Let's have a look about the results, about cycle time and quality. For this huge grinding process, basically we have a cycle time of 440 seconds, including loading, unloading. For the process, we are using oil as cutting fluid. And if you see the inner contour, the line shape, we reached the requested qualities. We are less than 50 microns. The straightness is less 5 microns, and the surface quality is less 0.34. So let's have a video of this grinding, entering, casting process. This is a front view of the VLC 350 GT. On the left side we have the O conveyor type with the pallets for the raw and finished parts. Here we pick up this housing, this cammering housing. Then we have to make a pre-radial measuring. There is a reference hole inside, and later the contour must be to a very small tolerance to this reference hole. Therefore it's necessary to make before this radial measuring. Here you see now the non-round grinding process, interpolation. The second process is now the face grinding. This is done with a self-sharpening specification, CBN specification. And now we start with the pre-grinding of the OD. That's the first step. Then we go to the measuring to check the diameter and give the information to the machine what's the stock for the finish grinding. That at the end we have a constant quality less than 10 microns for the OD. After the finish grinding, the workhead moves the part back to the unloading area and put the finished part on the pallet. So the next application is what I want to show you. This is a control plate which you can find in an axial piston pump. Here the dimension, you see this is a smaller part, OD with 71 millimeter. The material of this plate is 8CRMO16 hardened. And again, what we have to machine, it's colored in red. This is a face, it's a basic B. We have to do the grinding of the OD, and special here we have to grind the sphere. This is a radius, and the quality requirements are high for this sphere because this is a special function later in the pump. The surface quality RA 0.1. Then we have a run out of 20 microns to AB. AB is phase and the OD, and the area form contour error is only 4 microns. Here on the left side you see the stock what we have to grind. Diameter is 0.2 millimeter in the diameter, face 0.1 millimeter on the face, also 0.1 in radius. Which machine we are using? Now we are using also the VLC concept, but the smaller sister of the VLC 350 GT. This is the VLC 200 GT. Here again you see on the top of the machine the x-axis with the workhead and the clamping system. We have the z-axis for pick up the parts on the workpiece conveyor, and inside here you can see there are 3 spindle placed. On the left side it's an inclined OD grinding spindle. In the middle it's an inclined ID grinding spindle for grinding the sphere, and on the right side we have a motor spindle. This motor spindle take off the brush later to make brushing a deburring process. Here, very detailed, you can see the process chain. After clamping the part in the ID via a hydraulic operated clamping arbor here in the bore, we do first the grinding of the face. This is a corundum grinding wheel, no CBN, with diameter 400 millimeter. We use the same grinding wheel for grinding the OD, and then we start with the first brush process, and you see here this motor spindle takes a plastic brush which have abrasive grit inside. Why we have to brush this face? The requirements are it's not allowed to have small burrs on the edges on this side. As we have to grind on one side the face and on other the sphere, we have to put out now the part on the shuttle, external handover system, turn the part 180 degrees, then we clamp it again in the bore, and then we come to the second process chain. Basically, here you see number 5, grinding of the sphere. This we are using cut wheel with diameter 60, and the specification is a resin bonded silicon carbide, and the last process is again a brushing process with the same brush, plastic brush, to eliminate the burrs on this face. So here we have a nice view in the machining area. On the left picture you can see on the top the clamping system with the workpiece, and on the bottom side, on the left side, you see the OD grinding wheel, OD grinding spindle inclined position. In the middle you see the inclined spindle with a cut wheel for grinding the sphere, and on the right side you can see the spindle with the brush. Special here, we are using 2 different dressing tools for dressing. For the corundum wheel, For the OD grinding and for the face grinding, we use a rotation diamond form roll for dressing, and for dressing the cup wheel we have to dress the inner conical side to make the cup shape. We use a fixed single diamond. Why we can't use the form roller? The reason is, you see, we have a diameter 60 and we cannot go with this big diameter of the roller from the dressing wheel to go here inside. Here we get the result, cycle time and quality. The cycle time is 3.8 minutes, including loading, unloading. And let's have a look to the highest quality of the sphere. Basically, we reached this area form, the shape of 4 micron, smaller 4 micron. The runout was smaller 5 micron to A and B, and the surface finish quality at the end is also less than 0.1. With the next slide, I want to give you advantages of this VLC series, because this is also a typical EMAG pickup machine, and you get the automation included with the machine if you buy the machine. Why? Here the workhead has the function to pick up the raw part, bring it in the machine. Then we have different technologies, turning process or grinding process or brush process, and the workhead bring back the machine to the conveyor system. Therefore, you get the automation included. On the right side, you see 2 options which we can offer. On the bottom, this shows the machine with a shuttle automation. Shuttle automation move forward and backward the parts in the loading area, and normal, this shuttle is loaded, unloaded outside automatically by an automation cell. On the bottom side, on the right side, you see the conveyor belt automation. It cycles 360 degrees. Here you can place up to 20 pallets, and a normal operator put the parts manual on the pallet and take it away. Here we have an overview about the technologies which you can put in for some combination inside in the machine. It's, for example, hard turning, skiving, internal grinding, external grinding, cylindrical grinding, non-round grinding, honing or brushing process. So it's very, very flexible. And I want to end with this chapter with the advantage of this series. Basically what we learned, we can have a complete machining of the parts with different technologies in a single setup, so we get the maximum accuracy for the workpiece. Then the big advantage is again to use different technologies like turning, grinding, round or non-round grinding, milling, reaming or honing in the machine. Then you get the integrated automation. You have short distances. This means you get short chip-to-chip times. Then also this machine is like the most EMAG machines are vertical machines. It's perfect. The chips fall downwards. You have a small footprint here, because if you can do 2 or 3 technologies in one machine, then it's not necessary to buy 2 or 3 single machines. So you have a smaller footprint in your workshop, and the operator is possible to have a multiple machine operation. We have a perfect accessibility to the machine. If you open the front door, you have short distance to the workhead to change clamping chucks or clamping fingers, and also for change the grinding wheels and the dressing tools. It's very convenient for the operator. And if you have more machines in your workshop with this VLC concept, you have identical basic machines, and you have at least standardized operations and part programmings. So that's what I want to inform you about this machine series. And now...
Yeah, thank you, Manfred. We already find some questions from our audience in the chat. The first question: we already discussed in the German version of the webinar, I think a very good remark. Why is the diameter of the outer grinding wheel so small?
Yeah, the customer basically has two different workpiece types. One type is with the face quality RA 0.4, what we saw before the application, and one types have RA 0.2. And if you have RA 0.2 and a stock of 0.8 millimeter, then the grinding process can be not done in a single step. You need a rough grinding process and a finished grinding process with different grinding wheels. And therefore, you need already two spindles for rough and finished grinding of the inner contour, and the third spindle for the face grinding. And that's the reason why we have basically three small spindles inside, that the customer can realize also RA 0.2 quality. And this is an option or compromise. If you do the OD grinding, you have to use the small wheel.
Okay, next question refers to the NC programs. Do you use grinding cycles, or do the programs have to be written by hand?
Sure, we have for this machine fixed finished grinding cycles for OD grinding or ID grinding or inclined grinding, and we have also fixed dressing cycles for face dressing or for OD dressing. Sure, to finalize a complete NC program, you have to add to this grinding and dressing cycles the dimensions of the workpiece and also the technical grinding or turning data like cutting speed or feet and on.
Next question. Is an intermediate measurement of the diameter always necessary? Is it not possible to simply measure in cycles?
For this special application, what we show, the tolerance should be less than 10 microns. We have basically this intermediate measuring for each part, but this is not necessary for many other parts. This can be done also in a cycle, like to measure each 10 part or each 50 parts.
One more question about the measuring. What measuring tasks can the integrated sensor perform? Is it possible to integrate an external measuring system to make process corrections if necessary?
Yes. First, the answer to the first question. This measuring probe inside you saw, we can use for radial orientation in the reference hole for the camering. And this is also used to set up a new process. We want to have the first part already in quality. Therefore, we make a machining, a first step with stock, then we measure, and the second step is to finalize the workpiece. Then we get a process where the first part is already a good part. And for the second question, sure, after the machine you can place a post-process measuring unit or post-processing machine, and you have an interface to this machine, and then we get the measuring results from the machine and get a correction at the end on the machine. That's some standard.
Okay, I think this was the last question about this chapter. We will do a final round of questions at the end of the webinar after the summarization. I'd like to give you now a short overview about our software tool EMAG Contour, because we are working with non-round geometries, very complex parts where we have to deal with an interpolation of the rotating axis of the workpiece spindle and the infeed of our feed axis, the Z axis, to make sure that we have a very small deviation between the required contour of the workpiece and the ground part. Our software EMAG Contour can help us, because for the interpolation it is very important to take into account the dynamic machining behavior, because we have limited accelerations in the feeds. We have to avoid a swing up effect, So we have to choose not only the correct position of our machine axis in the NC code, we also have to choose the correct speed and acceleration to make sure that we have a smooth path of the grinding tool. EMAG is the answer to this challenge. EMAG uses as input the workpiece data from the customer and calculates for our different machining concepts the correct NC data, which is the output of this software. So EMAG Contour is the link between the drawing of the customer and the commands for the machine, that all the mechanical equipment and grinding tools do the best job to make sure that we've got a non-round geometry according to the requirements with a very short cycle time. This tool can also be used for our horizontal non-round grinding machines, for example, for the production of camshafts. So finally, I'd like to sum up the content of the webinar, what you heard in the last 45 minutes. We have learned that the market of high precision pump parts is expected to grow in the next years. One reason is that we have a wide range of applications, not only automotive industry, also commercial vehicles, agriculture and construction vehicles are an important market for high precision pump parts. EMAG offers specialized machining solutions for different ranges of geometries. The VG110 is the solution for the production of parts up to a workpiece diameter of 110 millimeters. It offers us a very small footprint and high accuracy for large batch sizes. The VLC series is the answer for bigger workpiece geometries, also with higher workpiece weight. The VLC series is a very flexible machine concept where it is also possible to integrate other fine machining technologies such as hard turning, brushing or honing. EMAG Contour is the software tool which helps us to find the correct NC data and uses as input data the customer's workpiece geometry. Make sure that we find the correct position, speed and acceleration for the machine axis. So this is a short overview about what EMAG can offer with regard to the machining of non-round workpieces. So finally I say thank you very much for your attention. We kindly invite you to contact us or our colleagues at EMAG LLC to discuss your machining tasks. And finally, I hand over to Jeff, our colleague in the US.
Yeah, thank you again. That was a great presentation. Thanks, Yannick and Manfred. We'll be hosting an open house. I hope you guys can join us. It's June 19th and 20th. So hope to see you there during our open house. Thanks for joining our presentation. Glad to have you. I hope you have a great day. Thank you.
Thank you.
Bye.
Hey guys. Thank you.